1 minute ago, Mount Etna, Europe's most notorious volcano, split open with a force scientists have never documented, spewing a strange, glowing material that defies every known geological rule. It isn't typical lava. An analysis shows it's not basalt, not andesite. Nothing ever found on this mountain or any volcano worldwide. The last time Etna changed this drastically, 7,200 years ago, a single collapse triggered a tsunami that raced across the Mediterranean. Now, seismic data is flashing red. An unexplained fissure, deep earthquake swarms, a record spike in sulfur gas. All signs Etna's structure is destabilizing fast. So what is this mystery substance? And could it be a warning that a disaster, even worse than we thought, is building beneath our feet? Rising more than 3,300 meters above Sicily's eastern plain, Mount Etna has long been both a landmark and a warning. Its summit, crowned with shifting craters, has witnessed centuries of eruptions, some routine, others catastrophic. Yet among all the stories the mountain holds, none cast a longer shadow than the ancient collapse that reshaped the Mediterranean coast 7,200 years ago. Hidden beneath farm fields and olive groves, geologists have found thick layers of sediment, marine sand and shell fragments, far inland from the present shoreline. These deposits, unearthed from Sicily to Malta and traced as far as southern Greece, speak of a tsunami so powerful it left scars across 3 countries. In the archaeological record, entire settlements vanish from one layer to the next, their disappearance matched only by the sudden arrival of ocean debris and saltwater silt. Folklore, too, carries echoes of this disaster. Old Sicilian ballads warn of the sea rising to swallow the land. Maltese legends tell of a day when the mountain fell and the water chased the people uphill. For years, these tales were dismissed as myth, but core samples and radiocarbon dates now confirm their foundation. In fact, a single event triggered by Etna's southeast flank giving way sent millions of tons of rock plunging into the Ionian Sea. The resulting wave swept inland, scouring the coast and reshaping the memory of everyone who survived. UNESCO's designation of Etna as a World Heritage Site rests not just on its beauty or activity, but on the lessons buried in its soil. The mountain slopes hold a record of cycles, of fire, collapse, and renewal, etched in ash and stone. Every generation has learned to read the signs: rumbling ground, sudden fissures, columns of smoke. Yet the evidence from 7,200 years ago proves that sometimes the warning comes too late. The ancient tsunami deposits are more than just geological curiosities. They are a stark reminder that Etna's most devastating threats can arrive without warning, and that the forces shaping the mountain today are the same forces that once unleashed disaster on an unimaginable scale. Now, as strange signals and unfamiliar materials surface once again, the question is whether history is repeating itself, or if the next chapter will be written in ways no one can yet predict. On February 8, 2000, the familiar rhythm of Mount Etna's unrest took a sharp turn. Early that morning, a fissure opened across the southeast summit, a raw wound stretching nearly 200 meters, steaming in the cold. Seismic stations at the Osservatorio Etneo, tuned to the mountain's every murmur, registered a sudden uptick. A swarm of earthquakes clustered deep beneath the summit, each one sharper and more persistent than the last. Most quakes in this region are shallow, tracing the restless movement of magma as it pushes upward. This time, though, the epicenters plunged to depths rarely seen, over 7 kilometers down, where the boundary between crust and mantle blurs. Within hours, gas sensors scattered along the upper slopes began to spike. Sulfur dioxide, a key marker of volcanic unrest, surged to levels not recorded in over a decade. At the main observation post, analysts watched as the readings climbed past 6,000 tons per day. The air around the fissure thickened with a biting metallic tang, and the usual white plumes took on a yellowish cast. Satellite feeds from Copernicus Sentinel-5P confirmed the anomaly, mapping a dense sulfur dioxide cloud drifting east toward the Ionian Sea. Deformation networks, webs of GPS receivers anchored into the rock, picked up subtle but unmistakable movement. The summit was inflating, the ground rising by several centimeters in less than 48 hours. Fiber optic cables buried along the rift zones flickered with micro vibrations. Each signal on its own might have been routine. Taken together, the pattern was anything but. The mountain's breathing had changed, and the usual playbook no longer applied. Inside the observatory, volcanologists pored over real-time data, comparing seismic waveforms and gas ratios against every previous episode in their records. The deep quakes, the rapid inflation, the sulfur surge. No recent event had combined these signals in quite this way. The lead analyst, Dr. Lucia Romano, called an emergency meeting. Her team debated the risks. The fissure was widening, the seismic swarm showed no sign of fading, and the volatile gas output hinted at magma rising from depths not typically tapped by Etna's plumbing. As night fell on February 9th, the decision was made. Despite the mounting instability, a field mission would be launched at first light to collect direct samples from the new fissure. Standard protocols called for caution, but the data demanded action. The mountain was breaking its own rules, and the only way to understand what was happening was to get closer, no matter the risk. At dawn on February 10th, the summit was shrouded in darkness and sulfur haze, the only light coming from the raw fissure that had torn across Etna's southeast rim. The air pulsed with the low growl of distant rockfall. A helicopter lifted off from the observatory pad, blades chopping through ash-laden wind. Inside, the lead volcanologist, Dr. Lucia Romano, checked her instrument pack for the third time. Eyes fixed on the readout, temperatures near the vent were holding above 1,200 degrees Celsius. The pilot's voice crackled through the headset. "If the wind shifts, we're out. No sample is worth a crash." Below, a new pyroclastic flow was already in motion. It moved with terrifying speed, over 140 kilometers per hour, devouring the snowpack and sending steam geysers skyward. The plume, a dense column of black and ochre, climbed to 6,500 meters, casting a shadow that stretched all the way to the sea. Sensors on the chopper's undercarriage registered radiation spikes and micro-tremors, each one a reminder that the ground could rupture again without warning. The landing zone was a narrow outcrop, barely stable, littered with hot debris. Romano and her team moved fast. Every minute on the slope meant another risk of being cut off by fresh flows. Ash stung their faces, and the heat pressed through their suits in waves. The fissure itself pulsed with a strange, shifting glow, brighter than any lava Romano had seen in 2 decades of fieldwork. She signaled to the technician, who braced a reinforced canister with tongs. The sample was scooped in a single, practiced motion, the material inside radiating through the metal, alive with color and heat. The helicopter lifted off just as a fresh surge of gas roared from the vent, scattering loose rock down the slope. Romano's voice, clipped and urgent, logged the sample's coordinates and time, 0746. As the chopper banked away, the team caught a final glimpse of the fissure, a wound in the mountain, still widening, still hungry. The sample, sealed and cooling in its container, was now the only tangible clue to what was happening deep inside Etna. Whatever secrets it held would have to wait for the lab. But the risk wasn't over. The mountain had given up a fragment of its mystery, and the price of that knowledge was still being counted. Inside the Catania laboratory, the sample container arrived still radiating heat, its metal casing faintly pulsing with a red glow. Chain of custody logs show the transfer completed at 0809. The technician on duty, Marco Bellini, suited up in reinforced gloves and a double-layered apron, keyed his badge and logged the time, 0812. Standard protocol called for a gradual pressure release, But the urgency of the readings, temperature holding steady above 1,200 degrees, demanded immediate analysis. The moment the outer seal disengaged, a sharp hiss filled the isolation chamber. Vapor burst outward, swirling with an iridescent sheen. Sensors flanking the chamber walls registered a spike over 1,400 degrees Celsius, well beyond the design limits of the containment suite. Bellini staggered back, clutching his wrist. Emergency protocols triggered. Alarms blared, negative pressure fans roared to life, and the chamber doors slammed shut, locking the vapor and the sample inside. Medical responders rushed Bellini out. His burns, while not life-threatening, left a stark reminder of the risks at play. Instrument panels began to fail in quick succession. The mass spectrometer returned null data, its software freezing mid-scan. X-ray diffraction patterns dissolved into static, and the thermal camera's display flickered, then went black. The sample's temperature refused to drop, defying all attempts at flash cooling. Even the negative pressure filtration system, designed to handle volcanic gases far more toxic than sulfur dioxide, failed to contain the vapor cloud. Every routine method, density, refractive index, even simple magnetic response, yielded no match to any known volcanic mineral. By late morning, an INGV spokesperson addressed the press. The material does not correspond to basalt, andesite, or any classifiable volcanic product. Its behavior in containment is unprecedented. Our priority is safety and further analysis. The statement offered little comfort to the staff still locked out of the lab, or to the scientists forced to watch real-time data flicker and vanish on their monitors. The sample, now sealed in a secondary containment vessel, remained untouchable. No peer-reviewed protocol accounted for a substance that refused to cool, defied every instrument, and left a technician in recovery. The only certainty was that the mountain had produced something science could not yet explain, and that the risks of further study were no longer theoretical. Moon tomography teams deployed their detectors across Etna's upper slopes, searching for answers that surface measurements could not provide. Over weeks, streams of cosmic particles passed through the mountain, each one mapped and counted, building a density portrait from the inside out. The results startled even the most seasoned researchers. Deep beneath the southeast crater, the muon flux readings revealed a vast region where fewer particles were absorbed than expected, an absence where solid rock should have blocked their path. Seismic arrays, meanwhile, sent pulses echoing through the same region. The returning signals came back thin and scattered, as if bouncing through empty space. Cross-checks with gravity and GPS data ruled out instrument error or superficial fractures. What remained was a growing consensus. A low-density volume, possibly the size of a city block, had formed in the heart of the volcano. Dr. Romano, the lead volcanologist, called it a silent zone, a cavity so deep that even the rumble of magma seemed to fade as it passed through. In technical briefings, she pointed to the density maps and echo signatures, tracing the outline of a hollow that defied previous models of Etna's structure. No one could say when it had formed or how stable its boundaries might be. But every dataset hinted at the same unsettling possibility. The mountain was hollowing from within, its foundations losing support in ways that no surface eruption could reveal. For the scientists monitoring these silent depths, the question was no longer whether the mountain would hold, but how much warning, if any, the next failure would give. 2 days after the lab incident, the eruption's fallout reached far beyond the realm of science. On June 4th, the offices of Vulcan X, a major mining consortium, filed a string of extraction requests with Sicilian authorities. The filings, stamped urgent, cited the potential discovery of rare metals, iridium, platinum group elements, hinting at economic windfalls in the billions. Internal board memos, later leaked to the press, revealed a scramble to secure exclusive rights before the scientific community could even finish its analysis. Volcan X's spokesperson described the eruption as a unique opportunity for national interest, but their language did little to calm the storm that followed. By February 15th, the southern flank of Etna became a line in the sand. Hundreds gathered at dawn, forming a human blockade across the only access road wide enough for heavy equipment. At the front stood Giulia Ferretti, a local farmer's daughter turned activist, whose family had worked these slopes for generations. Her voice rang out over the crowd. "This mountain is our ancestor, not a prize for those who don't know her moods." Protesters waved banners defending Etna's UNESCO status, while drone footage captured their standoff with security contractors hired by Volcan X. The blockade held for 10 hours, halting survey teams and forcing local officials to intervene. 3 days later, on February 18th, the debate spilled into Parliament. Lawmakers argued behind closed doors over emergency restrictions. Should mining be banned outright? Or would that sacrifice a chance at economic recovery? The Ministry of Civil Protection called for evacuation plans. The Ministry of Interior warned that panic could do more harm than the volcano itself. No consensus was reached. Outside, Giulia and her supporters camped in the cold, holding vigil as the mountain continued to smolder. The battle lines between profit and heritage, urgency and caution, had been drawn, complicating every step of the scientific response. No scientific journal has published a peer-reviewed analysis of the substance taken from Etna's fissure. The sample remains locked in containment, its properties unclassified, its risks unmeasured. For the research teams, the absence of answers is more troubling than any single anomaly. Gaps in the monitoring network are impossible to ignore. The summit's sensor grid, stretched thin by repeated equipment failures and hazardous conditions, leaves whole sectors of the volcano unwatched for hours at a time. Offshore, the eastern flank, where a collapse would race toward the open sea, has no permanent marine geodesy stations, making early warning for submarine landslides little more than guesswork. On land, only 2 muon telescopes are currently active, both hampered by difficult terrain and limited coverage. The INGV's coordination efforts have brought in backup instruments and international partners, but the reality is stark. The data are incomplete, the models uncertain, and the margin for error is shrinking. Without more eyes on the mountain, above and below ground, scientists are forced to rely on partial glimpses, not a full picture. The true nature of the threat remains just out of reach, suspended between what is known and what is only suspected. In February 2025, Mount Etna's monitors recorded a fissure and a sudden spike in sulfur dioxide, the highest levels since records began. Scientists extracted a glowing substance from the eruption site, which laboratory analysis confirmed does not match any known volcanic rock from Etna or other documented eruptions. Imaging with muon tomography revealed low-density voids beneath the summit, echoing the structural weaknesses that led to Etna's catastrophic flank collapse and Mediterranean tsunami 7,200 years ago. Yet as of June 2025, no peer-reviewed studies have classified the substance or fully assessed the risk of another collapse, and key seismic monitoring gaps remain. While mining companies and environmental groups clash over Etna's future, the scientific community agrees. Without more data, the true cause and potential consequences of these anomalies are unknown. For now, Mount Etna stands as both a warning and a mystery, reminding us that even the world's most studied volcano can still defy explanation.